Good morning. Cool to have you here. Happy Friday. Have a wonderful weekend. Let's get through this. On Wednesday, we were talking about techniques that are used to balance redox reactions. And a redox reaction is the big focus of this chapter. And in a redox reaction, you have to have something giving up electrons, which we call oxidized. You also have something to take the electrons, which we call reduced. And balancing redox reactions isn't too bad if you follow the steps we're going through. And on Wednesday, we talked about ways to do it in acid. And I'll review that a little bit here in a little bit too. And then at the end of Friday, we talked about balancing it in base. And balancing these things in base is totally possible and doable. But I get confused, and it's the very last part down here which gets me kind of twisty-turvy in my mind sometimes. We're going to get to the point where we're going to have a side which doesn't have enough hydrogen and or have a side that doesn't have enough oxygen. And you're supposed to add water to the hydrogen deficient side, and you add hydroxide to the oxygen deficient side. And if that works for you, this is an absolutely easier way to do these problems. But I'm also going to show you what I call Michael's method number 1 in this chapter, because for whatever reason, I have a problem. Like, I know water has more hydrogen per oxygen than hydroxide does and stuff, but it doesn't fit well with me. So I'm going to show you a longer way, but a way that does work better for me when balancing in base, okay? So we went through this example on Wednesday, and we'll just do it real fast. We have permanganate reacting with a weird peroxide to make an even weirder, arguably, MnO4 2- and also some oxygen. And when you're balancing redox reactions, you first want to split the reactions into the parts that look similar, all right? Now, you may not know if something is reduced or oxidized, and that's totally cool, all right? But hopefully you can see, like, you know, this and this have manganese, so they go together. And these weird things kind of look alike. I mean, this has oxygen too, but these look more alike than those two, I think. So try and just put the pieces that look alike together. And honestly, that totally works for these. If you want to get fancy, you can figure out the oxidation numbers of the two species. So like on this one, oxygen is going from -1 to 0. And on this one, manganese is going from +7 to +6. But underline, you don't have to do that, all right? It's an optional kind of thing and stuff. So at least put the two parts that look together, each other. And then after you put the two parts that look together, you want to balance them for mass. Now for the manganese, it's already done. Like there's 1 manganese on each side and 4 oxygens on each side. So that part's cool. But if you focus on the black parts right now, initially there were 2 oxygens and 2 oxygens, so the O's are okay, but this side had 1 extra hydrogen. So because we're in base, at the end of the day, we can only have hydroxide or water. So this is where this last part comes in. You add water to the hydrogen deficient side. So this side had just 2 O's and no hydrogen. That's why we added a water right there. But in the process of adding water, not only do we add 1 extra hydrogen, but we also add an oxygen. So because now this side has 3 oxygens and initially this only had 2, we do need to add a hydroxide to that side as well. And when you look at this then, now each side has 3 oxygens and 2 hydrogens, so it is balanced for mass. So again, the quicker way, I won't deny it, is to add water to the side that needs hydrogen and hydroxide to the side that needs oxygen. But I will show you an alternative way that you're welcome to use if you want later. Questions on any of this so far? Sweet. Once you balance them for mass, the next thing to do is charge. And this is why charges are so important in this section. So if you haven't been writing the positives and negatives, it's definitely time in this section to start, because you can see maybe why here. In this reaction, the mass is balanced, like the atoms on both sides, but the charges are not. So there's a -1 there and a -1 there. The reactant has a total of -2 charge. The product side initially has no charge. Both oxygen and water are neutral. So the only thing you can do to balance charge is add negative electrons. So you're going to add the electrons to the more positive side. That's one way that people like to interpret it. You can also just think of it like as a balance, and you have to have the same number of negatives. So the -2 on that side is now balanced by a -2 on the product side. Now both sides are balanced for mass and charge. And by the way, really all of our balancing of chemical reactions, they have been balanced for both mass and charge. We just haven't focused on the charge because it honestly wasn't that important. But in this section, you can probably see it is. The other one had a -2 on the product side and only a -1 on the reactant side. So remembering that we can only add negative electrons, we're going to plop one on the reactant side right there. Now we've got -2 on both sides. At this point, you should see electrons on opposite sides, all right? If electrons are on the product side, that means that something on the reactant side is losing them, so that's the oxidized side. And the electrons on the reactant side, those are gaining electrons. The reactant is gaining electrons, so that would be reduced. If you happen to see both electrons on the product side or on the reactant side, then just go back and check your calculations, because at this point they should be on opposite sides. And that's also why at first you don't really need to know which is being oxidized or reduced. If you follow these rules, the electron should pop out naturally, and you can tell really quickly. Yeah.
So can you never have electrons on just one side?
Yes, if you're, the kinds of things we're doing are full redox reactions. And if you had just electrons on one side, those would be like some kind of fancy, what I would call a half reaction, all right? And half reactions can be useful, but these, when you want to make a full, complete balance thing, George, then you'd have to have them on both sides. Anthony, I think it was on Wednesday, said how electrochemists and showing electrons is a sin, and that's pretty strong language for my G-rated class. However, electrons aren't usually shown, George, so that's why we're focusing on balancing and balancing stuff. But a half reaction, you could show the electrons, but that's a different kind of application. Good question. All right. Now that we've got the electrons, and because showing electrons is bad in chemistry, if we add these two reactions right now, you're going to have an excess electron on the product side. And like George and I's conversation brought out probably more eloquently than we need, we want to try and hide the electrons, right? We want to try and make them all go away. So what we're going to do next is we're going to multiply this reaction by 2, all right? And the only reason we're doing that is we want 2 electrons there. So in the final step, when we add them together, the 2 electrons that are products will cancel the 2 electrons that are reactants. So we're going to multiply that second one by 2, all right? And again, it's not because of anything that manganese is all about. We just don't want the electrons to show in the final step. And now, adding these two half reactions where electrons are showing together will give you an overall redox reaction where no electrons are showing, and this thing is what pops out. So again, the couple of things. In base, all right, you add water to the hydrogen deficient side and hydroxide to the oxygen deficient side. Second thing, if you're ever uncertain about your answer, go back and check, all right? So in my world, checking means balancing for mass and charge. So if you go through here, there's like 1 O, 2 O's, and 4 times 2, 8 O's. So that's 8, 10, 11 oxygens. And on the product side, 2 times 4, 8, 9, 10, 11 oxygens are balanced. So you can absolutely check the mass just like we've done before. But a new thing which is very helpful is you can also make sure that the charges are balanced on both sides. So what I mean by that, here's a -1, a second -1, and 2 more -1s, -4 on the reactant side. And if we've done this right, the product side should be balanced as well. No charge, 2 times -2, -4, everything's balanced. You can always go back and check yourself, and especially at first, that's probably a cool move. That works with acid and base and everything else. Okay, so if that method worked great for you, you can tune me out for the next couple of minutes because I'm going to show you an alternative way of balancing things in base. And again, I'm showing it to you because it makes more sense. I have problems doing the hydroxide water dance. I know like logically what I'm saying right there in the slide, but for whatever reason, when it comes down to game time, I fumble. Anyway, so I'm going to show you a longer way, but it works really well for me. And it's totally up to you which way you want to go. You don't have to do it this way. In my longer way of doing things, I'm first going to pretend that I'm balancing the reaction in acid. In acid, as we saw on Wednesday, you add H plus and water. Excuse me. And to me, that's easy, all right? You add H plus to the hydrogen side, and you add water to the oxygen side. But because it's in base, at the end, I'm gonna go back and neutralize with hydroxide. And what that means is in my final equation, can't have any H pluses. So I'm gonna add an equal number of hydroxides to wipe out the H pluses. H plus hydroxide makes water. So I'm going to end up with different amounts of water. I'll show you what this means. And again, this works really well for me, but you don't have to do it this way. So just like before, you show all the half reactions. That part hasn't changed. The next part, though, is we're going to pretend that we're balancing in acid. Now, like before, the manganese doesn't need any balancing because all the atoms are set. But up on this one, where I got kind of confused because I need to add water to the hydrogen deficient side and then hydroxide, blah, blah, blah. This is easy to do in acid, all right? I need an H plus. This side has one, this side doesn't. Bam, an H plus, balance, if it was an acid. Okay, so this part kind of saves me from thinking about the water hydroxide thing, but I'm going to have to do something here at the end. Now, continuing on, all right, you want to balance them for charge. That part hasn't changed. So 2 electrons for the first one, 1 electron for the second one. Got to make sure those electrons don't show at the end. We're going to multiply that second equation by 2, just like we did before. And then, now that we have 2 electrons on both sides, we're going to combine them. Now, notice there's an H plus there. So when we add the half reactions initially, this is what we end up with, all right? And this is balanced. You can double check that all the charges and all the atoms are the same. Notice on this side now we have 2 times -2, -4, but you subtract a +1, so it's like -3, which is what we have on that side. But you can't leave it this way because this is a reaction that they want you to balance in base, not in acid. So what we're going to do is for every H plus, we need to add a hydroxide because H plus OH minus makes water, all right? So for this one H plus here, I'm going to add a hydroxide to make water. But if I add a hydroxide to the product side, I need to add a hydroxide to the reactant side as well. In math, if you add 3 to one side, you have to add 3 to the other side. It's the same kind of thing in chemistry. All right, I'm adding something to both sides. So in this reaction, all right, I'm going to add a hydroxide because I need to get rid of that H plus. In base, you can't have H plus, you can only have hydroxide. But if you add hydroxide to the product side, you have to add hydroxide to the reactant side as well. Now the part in the box there, those are going to combine to make water, all right? So H plus OH minus makes water. I have a new hydroxide on the reactant side, and bam, we get the same reaction that we got earlier with hydroxide and water. The only difference is that we pretended it was in acid first and then went to base by neutralizing. So when you neutralize, all right, add equal amounts of hydroxide to both sides. You have to have enough hydroxide to balance the H+. So if we would have had like 3 H+, I would have added 3 hydroxides there and 3 hydroxides right there, all right? And the H+s and the hydroxides become water. Either way works fine. This way is a little bit longer, but like I said, for some reason it works better in my primitive brain. So, any questions on that? This handout has more examples and it talks more about it too. So if you're having questions on it and stuff, check it out and we'll see. When you balance reactions, these redox reactions, all right, the number one thing is just to see what kind of pH it is. If it's acidic, pH less than 7, then you just add H+ and water. If the pH is basic, i.e. greater than 7, then you would add hydroxide and water, or do the acid first and base. It's up to you. In the past, sometimes people have gotten messed up because they want to add things other than H+ and water and acid, or water and hydroxide and base. So you don't want to add O2 and oxides or H2 or anything like that. You can only add the parts that are restricted by your pH. All right, don't go crazy on me here. The ions, absolutely important. All right, you must write the charges here because that's how you figure out how many electrons there are. All right. So it's pretty chill. And again, at the end, man, if you ever have questions, all right, you can always check your work, all right? Check it to make sure it's balanced for charge and mass. If it is, good to go. Any questions on that? Okay. The reason we're going through these balancing redox reactions, is because there's some really interesting kind of chemistry applications that we can have, all right? This is an example of something we talked about on Wednesday called a direct redox reaction, all right? And what's happening here is a piece of zinc metal was placed in a copper 2+ solution. And those chemicals are ready to react with each other. These little silver globes right here, those are the zinc metal ions, and the little literally copper colored, I guess, those are the copper ions. And we're going to see in a little bit that zinc loves to give up 2 electrons, and copper wants those 2 electrons for itself. So after a while, zinc 2+ ions start going into solution, and on the face of the zinc metal, you'll start to see the copper metal form. It's usually kind of a red color. We would see the zinc strip, if you will, disappearing. It's not really disappearing, all right? The zinc are just becoming zinc ions, and you'll start seeing this copper metal. But if you scrape the copper off and stuff, it would appear that you're making zinc disappear. But remember, magic and chemistry, unfortunately, are different. And I forgot my magic wand at home. Anyway, so we can talk about this in terms of oxidized and reduced again, all right? I like the Leo the lion says grr, oil rig, whatever. Lose electrons means oxidized. So your zinc is losing electrons to make zinc 2+. Gain electrons reduced. Copper 2+ is gaining the electrons that zinc gives up to make copper metal. This is actually the reaction that if you took Chem 221 with me in the fall, this is what the empirical formula reaction was all about. You essentially were placing strips of zinc in a copper 2+ solution. You collected the copper. It felt like the zinc disappeared because the mass of the zinc was left at less after you put it in. So, oh boy. Anyway, here's a reaction. Nickel and silver ions are reacting to make nickel 2+ and silver. Now, which species in this reaction is the reducing agent? And I put this up here just as a quick reminder. Reduced means gaining electrons, but reducing agent is the thing that allows something else to be reduced. Reducing agent is something that's being oxidized. So if you see the agent, just remember it's kind of the opposite, which I hate, all right? I'm just the messenger here. I didn't make these rules, but reducing agent is basically asking like which one is being oxidized. Now, if something's oxidized, it's going to be more positive on the right than it was on the left. So we're only going to consider the nickel and the silver plus for this reaction. We're not going to consider the products. Only look at the reactants. Does nickel become more positive or does silver become more positive? That's right. The nickel is going from nickel 0 to nickel plus 2, all right? So that would be a sign that it's being oxidized, it's losing electrons. Silver is going from positive 1 to 0, all right? So silver plus is actually gaining an electron. It's becoming more negative, all right? And that's another way you can think about these kind of things. So if you see a question like this, only look at the reactants. The agents are like the opposite, so reducing agent is oxidized, oxidizing agent is reduced. And you can look at just which one becomes more positive if you like, or any questions on it? Okay, so that was a direct redox reaction, and those are really high yields. If you're creating copper metal, for example, that's a really good way to make it because the percent yields are almost not quite 100%, but they're pretty close. It's called a direct reaction because both the oxidizing and the reducing parts are put directly in contact with each other. So again, if you're making a compound, or in this case, if you wanted to make copper, very high efficiency, all right? Like a lot of times when you make things in lab, you know, you'll have much less than 100%. Most of these are pretty close to 100%. That's why in the Chem 221 lab, we like doing it. Percent yields are high, sometimes too high if the stuff is wet, but that's another story. Anyway, direct redox reactions, really powerful, usually pretty fast. But there's no control, all right? We don't really have any control unless we physically take the zinc metal out, all right? And that's okay if you're making things, but there's more you can do. So what we can also do is separate the oxidized and reducing species with essentially a types of wires, all right? Or types of racing tracks, if you will, that the ions can go through. And this is where Galvani and Volta, the two original scientists, did that. And what they found is that certain combinations, you make these things separate a little bit, you can actually record like a voltage. For us, electricity and voltage is nothing more than moving electrons, all right, electrons in motion. So if you have the electrons moving around, that means it's product favored, which we'll come back to later. Product favored just means you have galvanic or voltaic cells. So you do something and something happens, all right? It's like if I push my remote control, I want the laser beam to come on, that's good, that's product favored. If my battery was dead and I pushed it and nothing happened, that would not be galvanic or voltaic at that point. That would be something else. We'll talk about that later too. So, a battery, which is really what we're kind of getting at here, a battery is just separating out the oxidized and reducing species. Now, unless you have current flowing, all right, the oxidized electrons can't get to the reduced side. So what people have developed is a really fascinating kind of thing. And imagine, if you will, that we're on like a little race track, all right, for our cars or trains or whatever you want to use and stuff. This way that I'm circling, this is actually how the electrons are traveling. Now, electrons are going to come from that part that's being oxidized, and that's still the zinc going to zinc 2+, that hasn't changed. But instead of the electrons going right to the copper ions, what we're going to have them do is we're going to have them go on a piece of wire, all right? So we're using a big piece of the oxidizing part, the zinc or the reducing agent, all right? And it's connected to a wire, something like copper, which is good at transferring electrons. And we're going to have it go to another piece of copper over here. Those electrons are going to go here, and this solution has copper 2+ in it. All right? So the electrons are traveling on this little circuit through the metal. They make contact with the copper ions over here. So this side is where the reducing is happening. Copper metal will start to appear. Now, you can't add copper 2 plus by itself. It has to be complexed with something else. There has to be some kind of negative ion. In this example, someone put copper 2 sulfate in, which is great. You could have used copper 2 chloride or whatever, okay? As the copper ions make copper metal, all of a sudden now, this side is losing positive charges. And negative charges don't really like to just be by themselves. So what scientists have created is something called a salt bridge. And a salt bridge is literally like a type of a seaweed that's been saturated in water. All right, it's nasty, smelly stuff. Agar, sometimes people cook with agar flakes. All right, drop that back on. Anyway, it's basically a way that ions can move from one side to the other. And why they're moving is that over here, as the zincs give up their electrons, they start making more and more positive charges. So you can imagine if you didn't have this salt bridge, zinc would make the electrons, but then all of a sudden there's a lot of positive charge right here. And as electrons were formed, they might go back to the zinc. There wouldn't be a lot of movement. On this side, assuming electrons get through, the copper ions start disappearing, you'd end up with a big negative charge. So the negatives over here are going to travel through the other side to connect with those positive zinc ions. So the negative charge is going on the anions, in this case sulfate. And it's a big negative ion, so it's like electrons moving. It literally is a circuit, all right? We have pure electrons in this part, and then the anions right there. It keeps everything going, which is just crazy. Why this is cool is that now we have the choice to make the reaction occur or not occur. It's like a switch, like my button on my remote control, all right? We want the reaction to go, turn it on. Don't want the reaction to go, need to go to the library and study those journals, turn it off, man. No problem. Batteries are just about the control of chemical reactions, and it's a pretty powerful thing. I would argue that every one of you probably today have used a battery at multiple times, you know, calculators, cell phones, your cars, whatever and stuff. This is how they work. So let's look at some terminology here going on with these batteries. First of all, there's always going to be a site of oxidation where the electrons essentially are coming from. These oxidizing species get special names when it comes to batteries, and the most important one is anode, all right? An anode is just where the electrons come from, all right? It's the source of oxidation. A lot of times on batteries, including like your AAAs and AA's and 9 volts and stuff like that, you can buy at Fred Meyer's, they'll have a positive and a negative. The oxidation site is going to be negative. It's the source of electrons. Electrons go towards the positive side. They come from the negative side. Now, on the other side where you have the reduction, all right, that's called the cathode. So the cathode is the fancy name for where the electrons are going to, where you get this movement of electrons. And the sign of the cathode is positive. Electrons which are negative go away from the negative side and they go towards the positive side. Now, a quick way to remember oxidizing and anode, all right, is that O and A are both vowels, all right? A, E, I, O, U are the 5 vowels, sometimes Y. Oxidized and anode go together. On the other hand, reduced and cathode are both consonants, so they go together. Anyway, this is one way to think about how this all works. The anions will float from the cathode to the anode. We're not going to worry about this, but you do need a little positive charge going back just a tiny bit. Don't be too worried about that. But I do want you to see that the anions continue the flow of electrons, basically, keeping the circuit going around. This salt bridge is really important. Again, it's basically just seaweed, nothing you have to worry about. I've made them before. They're not difficult. They do smell, in my opinion, but that's my aesthetic here talking. Anyway, we have to keep the electrons moving. Otherwise, you'd have a buildup of positive and negative charge. But if you do it this way, man, it goes through, right? And we'll talk about ways to make them more effective, less effective, stuff like that. Now, some people like my vowels and consonants, and some people don't. So let's talk about alternatives. And my favorite one is probably the red cat. Poor kitty. Anyway, reduction, cathode, red cat. Okay. On the other hand, an oxidation at the anode and stuff. So these are cool. Sometimes they're called the red cat and an ox. If this works for you, cool, that's fine. Remember that oxidation is the same as reducing agent, so reducing agent is not the same as reduced, and reduction is the same as an oxidizing agent, so red cat and ox, vowels, consonants, whatever, freedom to choose, Pepsi or Coke. Anyway, questions? Good. Now, writing out a battery with separate diagrams and stuff would be really confusing. So there is what they call the shorthand notation for these, and it's going to look something like this. And it's not too hard to figure out. We're going to break down what all these symbols mean. But instead of writing out, two different compartments and the wire and the cell bridge and stuff like that, once you are able to interpret this is like a shorthand way of doing it. Now, we saw earlier how zinc is going to zinc 2+, that's the site of the oxidation. And we also saw that copper 2+ is taking those electrons to make copper. So in these kind of diagrams, electrons always flow from left to right, from the site where the oxidation occurs to the site of the reduction. Or, if you want to be fancy electrochemist, from the anode to the cathode. So the anode, the oxidation is on the left, the cathode, the reduction site is on the right. And you can see that the electrons come from zinc, and then you end up with zinc 2+. Excuse me. The electrons start at copper 2+, and they make copper metal. The single lines and the double lines have a meaning. The single lines is like a phase boundary, and so what that means is you're going from a solid to a solution, or in this case, from a solution to a solid. I like to think of it as like a before and after picture for both the anode and the cathode, but that's just me. And this little double line here, you can think about it as the thing that separates them two. So it's like the salt bridge, or you can think about it as the wire, doesn't matter. The important part is that you have electrons going left to right, oxidizing to reduction, or anode to cathode. Cool. Fat cat. Again, this electrochemistry that people have, whatever. Fat cat means electrons flow from the anode to the cathode. I don't know. I like cats, so really I do. You wouldn't think it after showing red cat and fat cat, but really they can be helpful and stuff if you're learning, which is cool. Any questions? Remember that every battery you use today or any time is going to be able to write something like this. And we'll talk about some of the common ways at the end of this chapter. Here's an example of a reaction cell. All right, galvanic just means a battery that works. You can see there's copper and copper 2+, and on this side there's chlorine and chloride. Now electrons flow from left to right, from the oxidized side to the reduced side, or from the anode to the cathode, all right? So the copper 2+ is where the anode, where the oxidation is. So you could literally write it as copper going to copper 2+, gotta have 2 electrons to make the half reaction balanced. Sometimes the solutions will have a concentration in them. This is a 1.0 mole per liter solution. And then this side, when you pass through the phase boundary, that's where the reduction is going to occur. That's where the electrons are going. And you can see how chlorine doesn't have a charge, but chloride does. So in this reaction, chlorine is being turned into chloride. They usually don't include the stoichiometry, so we can put that in to balance it. And then 2 electrons are needed to balance the charge. It also says that how this solution has a 1 molar solution concentration, at least to begin with, and the pressure of the gas is 1 atmosphere. Atmospheres are what they use for pressure. Now, in this sense, because we have a gas and a solution, we need something to deliver the electrons. All right, electrons are usually metal. So the platinum right there is just a way to say that we're getting the electrons to the chlorine via a platinum electrode. Electrodes are often made of platinum, nickel, sometimes palladium. All right, platinum is very inert. It's not the cheapest metal, as you can probably imagine, but it is a good way to get the electrons to your thing. Any questions on that? Okay, so
In a voltaic electrochemical cell, an oxidation occurs at an electrode called the anode. The electrons released at the anode travel through a wire to another electrode called the cathode, where the electrons are consumed in a reduction reaction. Anions are then shuttled through a salt bridge from the cathode compartment to the anode compartment. Otherwise, a net negative charge would build up in the cathode compartment. The negative charges move in a circuit through the cell.
So you can see here then that in this reaction, copper is creating copper 2 plus, and this is the anode where the oxidation is occurring. And the electrons are getting over to this side where silver plus is being turned into silver metal, all right? Now in the previous examples, the anode was on the right and the cathode was on the left. You don't have to do it that way. This particular diagram is the reverse of it. So in this one, the copper over here is creating the electrons. Electrons are getting away from the negatives. Negatives repel each other, and they're going to the positive cathode on that side. Now, notice this number up here, that's a voltage, and we're going to talk about that here in a little bit. And some reactions create more potential, if you will, or more energy than other ones. We'll talk about this, but the punchline here is that positive volts make reactions occur. Those are the batteries. When you want them to do something, they do. So my remote control, my little red button right there, it's got a positive voltage of some value. If I push the button and nothing happened, then that would mean I'd have at least 0 or even maybe a negative voltage. But we'll talk about that in a little bit. Any questions? Which of these species is being oxidized? All right, so this is back to the shorthand notation, all right? If you're looking for a species that's oxidized, it's going to be either the zinc or the gold here, the gold plus. And electrons always move from left to right. So what that means here is that the zinc is giving up electrons to make zinc 2 plus. So if zinc is giving up electrons, it's being oxidized. We would say in this reaction that zinc is being oxidized. Remember, electrons go from left to right, from the anode to the cathode in these kind of shorthand notation versions. Okay. So again, if you have a product favored, which just means galvanic, then electrons will flow from the side of the oxidation to the side of the reduction, or from the anode to the cathode. And again, for these kind of reactions, the anode will be negative, electrons are coming from there, and the cathode will be positive, electrons are going to that side. All right, and again, I just want to focus on a galvanic or voltaic cells are just batteries that work, all right? You put them together and something happens. There is another kind of cell called an electrolytic cell, and those kind you put together and nothing happens. But we're going to see that with a little electricity, you can do wonderful things. So electrolytic cell is when you put these things together, but nothing happens. And there's actually a use for that. We'll talk about that here in a little bit. But mostly what we're focusing on are the batteries that work, the ones that work in your calculators and cell phones and iClickers and stuff. So now, next thing we're going to talk about here is why some reactions happen, the galvanic and voltaic, and other ones, the electrolytic cells, don't. And I'm going to use the example of a waterfall. All right, if you've ever seen a waterfall in the climbing boards or anything like that, I'm sure you've admired their beauty. But Water always goes from the top to the bottom, all right? I have yet to see myself anyway, an example of water going from the bottom to the top, which would be fun, but that's the way it goes. So there's a reason, an energy reason, why the water goes top to bottom and not bottom to top. And believe it or not, this is a good analogy for these electro cells, these galvanic and voltaic cells as well. Like some reactions, they will occur. The water goes from the top to the bottom. The reactants will go to the products. On the other hand, some combinations and stuff, if you start at the bottom, it's going to be difficult to go back to the top. I'm not going to say impossible. Just like with a waterfall, you could have some kind of a water wheel or something and get the water up there if you really wanted to, but it would be difficult. So electromotive force is like the equivalent of figuring out if the electrons are going to occur. Will water go downhill or will it not occur? Like, do you have to make them go up? Electrons spontaneously flow in one direction only. Now, in the last chapter, we saw how spontaneous means that delta G is negative, the reactions that are going to occur. So spontaneous just means it will occur by itself, and there's going to be one way in which the electrons will flow, and there will be one way in which the electrons don't flow naturally. This is an example again of a zinc-copper system. The zinc is giving up electrons to the copper ions. The electrons are flowing this way. This is kind of a little animation right here. This is the connected cell, and this is the cell when it's not connected. So notice that in the second little picture there, they just disconnected that one terminal. This is like the wire that's right here, okay? And they literally just took the wire off the piece of metal. And notice how this number changes. Now it's kind of hard to see here, but that's 0 volts. This is 1.1 volts when it's connected. So when nothing happens, you have 0 volts, and when it's connected, you have 1.1 volts. That little device is called a voltmeter. In physics, you'll probably use it more, definitely. But it's a way to measure if the electrons are flowing or not. So the voltage is related to this electromotive force, this EMF, all right? So if EMF is a positive number, like this one, that's like water going down the waterfall, all right? It's going to happen. These are the batteries that work. On the other hand, you can get, as we're going to see, like negative values, negative voltages, and those guys you have to kind of force, and we'll talk about ways to force them later. Now, EMF is a really powerful thing when it comes to this section.
You're unbelievable.
Am I dating myself? Does anybody know this song? It's EMF? Okay, good. Suzanne's looking at me like, what the heck? All right, this was a really popular song. The band was EMF, all right? And you are unbelievable. Okay, enough of the positive. So anyway, hopefully you remember now EMF and stuff from this. You can YouTube this song later. Anyway, pop that back on. EMF is just a way then stuff to measure if something's going to happen. All right, so this voltage thing, pretty important, all right? So with this reaction, if you're under standard conditions, 25 Celsius, concentrations 1 mole per liter, your cell voltage, your EMF, 1.10 volts. Now, volt is a new type of unit. It's something that's used a lot in physics. A volt is 1 joule per coulomb, all right? So joules are like energy and coulombs are like charge. So it's a way to relate the energy, if you will, to so much charge. We don't have to worry about this so much. Just if you see the volts, they're going to be really handy in this section. And if you talk about types of batteries from Fred Myers, all right, like those little square batteries, those are 9-volt batteries, all right? That's what it is, all right? It's 9 joules per coulomb, all right? So we're going to start talking about voltages. All right, notice here all these things, all these delimiters, 25 degrees Celsius, 1 moles per liter. You have to know your conditions at which you're measuring the voltage, the cell potential. And by the way, cell potentials usually get the symbol E. An E naught means E at standard conditions, all right? So just like delta G and delta H and all those dudes, they could be measured under standard conditions when they have the little zero. This E0 is something then that just means you're measuring things under standard conditions too. So E naught usually means 1 mole per liter, 25 degrees Celsius. If you had a gas, it would be 1 atmosphere of pressure. All right, all of the kind of things we've seen. And those E values or E naught values are going to be things measured in volts. So we'll write a lot of V's and stuff here. Okay. It would be nice to calculate the cell voltage of a reaction like this, all right? And if you knew the individual half reaction cell voltages, then you could add those two numbers up to give this number right here. And the way that scientists have discovered these values of voltages is they created, if you will, like a ruler stick, all right? Now, in length, all right, the meter stick, which I happen to have here, right? The meter stick is the way to measure everything, all right? So you can measure this table. If you have a smaller value, you can measure the length of your, thermometer or whatever. But from everything of length, the ruler is what we use, okay? If we need something like that for cell potentials, all right, we need like a ruler stick to define other reactions, all right? Once we all define the meter, then you can measure anything based on it. So in cell potentials, there's something called SHE, the standard hydrogen electrode or standard hydrogen cell. And this is the ruler by which we measure all other voltages, and we'll see examples of this. So scientists got together and they let this one equal 0 volts, so they calibrated it. And it's basically just H plus acid at 1 mole per liter going to hydrogen gas at 1 atmosphere of pressure. And we're going to see that it works both ways. So if hydrogen goes to H plus or H plus goes to H2, the cell potential is defined as 0 volts. And from this, I'll show you how, they were able to figure out all these other cell potentials. So we're going to look at how we can use the SHE electrode then to measure like the copper reaction and the zinc reaction. And from there we can take this copper and zinc separately, put them together to find the cell potentials. So this is a reaction where we have zinc ions and zinc metal, and we have hydrogen ions and hydrogen gas. Now, when someone measures the cell potential of this thing, it's positive 0.76 volts. And notice how this is the negative terminal and this is the positive. So electrons are going from the zinc over here to the hydrogen side. So electrons are adding to the H plus to make hydrogen gas. So the left side in this diagram is where the oxidation is occurring. And you can probably imagine then the right side is where the reduction is occurring, all right? So in this problem, all right, the overall cell is positive 0.76 volts. This one is defined as 0 volts. That's what we scientists collectively all came together, well, not me personally, but we came together and decided that was going to be 0. We can use those two pieces of information to find the value of the zinc going to zinc 2 plus. So you can imagine, if you will, we know that the SHE electrode defined as 0 volts. And the overall reaction, which can be measured, positive 0.76 volts. So X plus 0 equals 0.76. That means that the half reaction, zinc going to zinc 2 plus, has a value of positive 0.76 volts. It's very clever how they came up with this. I must admit, I thought about this a lot actually. So this is a way that you can figure out the cell potential for these half reactions for when the electrons are shown. So zinc going to zinc 2 plus has a value of positive 0.76 volts. We would also call zinc a better reducing agent, i.e. it wants to be oxidized better than hydrogen, because you could also have hydrogen giving up electrons, but that's not what's seen. Zinc is giving up its electrons to be zinc 2 plus. We'll see this more on Monday. Okay, We can do the same thing with the copper's thing, but on this side now, notice how now the She electrode is the negative terminal. It's supplying the electrons, and it's going to the copper side, so copper 2 plus is taking those electrons to make positive or neutral copper. The cell potential for this reaction, 0.34 volts. So what this means then, just like before, 0.34 volts equals 0 plus X. We're going to solve for X. So you can probably imagine then that just like before, copper 2 plus going to copper is going to equal 0.34 volts. So then finally, if you take our new zinc reaction and our new copper reaction, where we know the half cell potentials now, the 0.76 from earlier and the 0.34 we just looked at, we can combine those two together. It gives the overall reaction, copper 2 plus plus zinc, going to zinc 2 plus plus copper, cell potential, positive 1.10 volts. So notice how if you add the half reactions together, you literally add the cell potentials together to get the value. So in this case then, the cell potential would be positive 1.10 volts. Questions? Before we leave, this is an example of a reaction between nickel and nickel 2 plus, and we want to find the cell potential. Now in this case, nickel is a reactant, and here's nickel as a reactant. Mercury 2,2 plus is a reactant, and in this reaction, mercury 2,2 plus is a reactant. So if we combine these two reactions together, we're going to get this reaction overall. So the cell potential will literally be just those two added together, 0.79 plus 0.25 volts. This is kind of the value you'd get if you had a battery made of this stuff. It would be nasty and toxic and stuff, but you could do it. This would be the way you can figure it out. Questions? All right. On Monday, we'll start looking at tables of reduction potentials and how you can use them to find different values. But man, for right now, have a wonderful day. I'll see you all on Monday.